And let me present our joint work with Professor Jan Hamhalter from Technical University in Prague. And the talk summarizes the recent results on the spectral order on A-star algebras and phonomial algebras with the following aims. To present a non-orthodox order on operator, what can replace the standard order and has an interesting physical content. To show what the most natural context for studying the spectral order is given by abstract A-star algebras. To demonstrate what the spectral order organizes operator effect algebra into a complete lattice, but naturally contains projection lattice as a sublattice, and to present the deep results on symmetries of a spectral order, what can be viewed as generalization of famous Wigner's and Dye's theorems on symmetries of quantum systems. The sequel B of H, we will denote the star algebra of all bounded operator acting on the Hilbert space H, and we know the standard order on bounded self-adjoint operator. In terms of Hilbert space quantum mechanics, it means that expectational value on observable A is less than expectation value of observable B in every state of a physical system. And this order is far from by lattice order. If dimensional Hilbert space more 1, then self-adjoint part of B of H is an anti-lattice. In the sense that suprema and infima exist only for comparable elements. And we shall need concept of a spectral resolution. Let A in self-adjoint part of B of H, and there is a unique system of projection called a spectral resolution of A, but satisfies the following condition: monotonicity, right continuity, boundedness, and for condition. There is a one-to-one correspondence between bound and self-adjoint operator and spectral resolution satisfying first, second, third conditions given by integral. The spectral order was introduced by Olsen and Raupen Arveson. It has many applications in matrix theory, operator algebras, and foundation of quantum theory. It is based on pointwise ordering of a spectral resolution. Spectral order is defined on self-adjoint operator as follows: A comparable in spectral to B if projection E lambda of B less or equal E lambda of A for every lambda. And in physical terms, inner product E lambda of A xi, where xi is a unit vector in Hilbert space H, represents the probability that observable A has value less than lambda in every state xi in the system. And therefore, spectral order, if for every state of the system and every real value lambda, the chance that observable A has value less than lambda is greater than the same chance for observable B. If M is a part of B of H and is a phonomial algebra, when operator from self-adjoint part implies that projection E lambda of A in M for each lambda. Zone can define the spectral order on the self-adjoint part of phonomial algebra, and the spectral order has intensely been studied in the framework B of H or for normal algebras. However, the most natural setting for the spectral order seems to be category of A-star algebras, and we will explain in the next next section. For normal algebras can be defined as sister algebras having a predual. Another way on looking at for normal algebras is to view when a subalgebra of B of H when equal to its double commutant. There is no characterization referring only to intrinsic property of the algebra without using dual structure or representation on a Hilbert space. This motivates Kaplansky to define algebraic generalization of normal algebras called A-star algebras. Let P of A be a set of projection on a sister algebra A, ordered by a standard order with orthogonality relation. A is called A-star algebras if the following two conditions are satisfied. Every maximal abelian sister subalgebra of A is generated by projection, and every non-empty subset of set of projection consisting of mutually orthogonal projection has supremum. If A is a A-star algebra, then the following holds. A has a unit, and set of projection is a complete orthogonal lattice, and every maximal abelian sister algebra of A is an A-star algebra. We can see that every phonomial algebra is a A-star algebra, but the reverse implication is not true even in the case of abelian algebras. A is an abelian A-star algebra if and only if it's isomorphic to an algebra of continuous function on a compact housed of Stonian space. And motivation for A-star algebra from the point of view of Boolean algebras theory is the following correspondence. The map A to sets of projection with order orthogonality relation 0 and 1 is one-to-one correspondence between abelian A-star algebras and complete Boolean algebras. This is not true for normal algebras since they are complete Boolean algebras, not isomorphic to any normal projection lattice. For every self-adjoint element A in a A-star algebra, there is a spectral resolution with the same properties in the case of B of H. And this allows us to define the spectral order on self-adjoint elements of A in this relation. Let me present some examples. If X is a Stonian space, F and G continuous function on X, when F comparable in spectral G, if and only if F of X less or equal G of X for every X in space. If P, Q are orthoprojection, when spectral comparable and classical comparable are equal. And if P, Q is this form, when P comparable Q in standard, but P not is comparable Q in spectrum. We shall mainly concentrate with a spectral order on the positive part of unit ball. The structure is now as operator effect algebra. And let A be two effects of A. When A comparable to B in spectral implies A comparable B in standard. And if A and B commute and A less or equal B, then A less or equal B in spectral. relation spectral order does not imply what A and B commute. As the following proposition demonstrates, the following statements are equivalent. A is abelian. A less or equal B in spectral implies what A and B commute, and relation standard order and relation spectral order coincide on effect algebra. Remarkable property of a spectral order is the fact that it organizes effect algebra into a complete lattice. If A is a A-star algebra, then effect algebra of A with a spectral order is a complete lattice with lattice separation are given in the following way. The formula for infimo simplifies in the case of finite A-star algebras. This is precisely the case when P of A is a complete modular lattice and so enjoys continuity geometry. If A is a finite A-star algebra and A and B two effects, then infima A and B in spectral has the spectral family this form. And if A is a A-star algebra, then a lattice of orthoprojection with standard order is a sublattice of lattice effects with spectral order. And what is where spectral order is the right order for studying logical structure of effects. And center of a lattice is usually defined as the set of elements satisfying distributivity law with any choose couple of elements. And elements Z in effect algebra is said to be central if for all x, y from effect algebra we have this equal. The set of all central elements is called the spectral center, and it is denoted by this symbol. Center of algebra it is a set of elements who commutative for all elements of A, and for finite A-star algebra we are able to characterize algebraic center in terms to the spectral order. And main part of my talk we shall mainly concerning with transformation, preserving spectral order and orthogonal relation. Projection lattice is a orthomodular lattice with orthogonality, and spectral lattice has a relation to orthogonality too, and projection lattice is a substructure of a spectral lattice. First, we look at the symmetries of a projection lattice. We will describe some definition. Bijection phi from set of projection of I to set of projection of B, preserving the orthogonality in both directions, is called orthoisomorphism. And a linear bijection G between two C-star algebras is called Jordan star isomorphism if G of square A is G of A square, and for two-second relation is 2. Every orthoisomorphism is an isomorphism in the category of orthogonal lattice, and every Jordan star isomorphism restricts to orthoisomorphism between projection lattice. The following theorem is very deep and completely characterize orthoisomorphism for heavy-star algebras. Yanham-Halter theorem. And let A be a heavy-star algebra without a type 1, 2 direct summand, and B an heavy-star algebra when for any orthoisomorphism phi, there is unique Jordan star isomorphism G, such that phi of P is G of P for all orthoprojection. In other words, P of A encodes the Jordan structure of A. This result generalizes die theorem if A is a phenomenal algebra, and so Wigner theorem when A is B of H as well. The main goal of our investigation was to describe symmetries of a spectral lattice. Let A be a heavy-star algebra. Bijection phi from effect to effect algebras is called a spectral automorphism if phi preserves spectral order and orthogonality in both directions. Unlike the projection lattice, not all spectral automorphism are restriction of Jordan star isomorphism, since might be non-linear. So spectral automorphism do not restrict to orthoisomorphism. And we present some example of spectral automorphism. Functional example and Jordan star isomorphisms example, and some interesting map. And third example, this map not preserving multiples of a unit. We say the spectral automorphism preserves multiple of a unit if there is a surrogate function phi, such that it is mistake. Sorry, f lambda 1 is f lambda 1 for every lambda with sets. If we have main theorem, let A be a heavy-star algebra without type 1, 2 direct summand, and let phi be a spectral orthomorphism preserving multiple of a unit. When there is a unique Jordan star isomorphism G and unique increasing bijection F, such that phi of A is GFA for all effects of A. Each spectral automorphism that preserves multiples of a unit restrict to an orthoisomorphism of a projection lattice, and each spectral automorphism acting as identity on the multiples of a unit extend to a Jordan star isomorphism. Heavy-star algebra is called factor if its center consists of multiple of a unit. Our result of a structure of spectral center says the spectral isomorphism must preserve the centrum of finite algebra. Especially in case of factors, it must preserve automatically multiples of a unit. And we have a next theorem. Let A be a finite heavy-star algebra. Let phi be a spectral automorphism of effects. When there is a unique Jordan star isomorphism G and unique increasing bijection F, such that phi of A equal GFA for all effects. Spectral automorphism are naturally induced by spectral lattice automorphism. The idea behind it's that any such automorphism tau transforms spectral resolution into spectral resolution. Let A be a vector algebra. Let tau be spectral lattice automorphism of projections. When we map phi tau on effects defined with equal for all elements of effect algebra is a spectral lattice automorphism. To what extent to the spectral automorphism determined by projection lattice automorphism, and we have answer for normal algebras, and it is with theorem. And another direction is the study of spectral automorphism of general safe agent, maybe not bounded operator. There is a one-to-one correspondence between safe agent operators on a Gilbert space H and spectral resolution, which on to define the spectral order in the same way as in the bounded case. And we generalize the results by Lausch-Molnar and Schemmel obtained for positive construction on B of H in the following way. If we will have positive self-adjoint operator acting on a Gilbert space H, and P of H is a set of projection acting on H, and main result in this case, let phi be a bijection preserving the spectral order in both directions. When there is a positive number C and spectral automorphism tau on P of H, and strictly increasing bijection F, such that phi have this form. Thank you very much.